The problem is to find out what type of conic section the following quadratic form represents and transform it to principal axis. Here q is equal to 17x1 square minus 30x1x2 plus 17x2 square, which is equal to 128. We know that the quadratic form q is equal to x transpose ax. Here x is a column vector which is equal to x1 and x2. So the elements of x are x1 and x2, and A is the symmetric coefficient matrix. In our problem, A can be written as a matrix. Within matrix, A11 element is 17, and to find out A12 and A21 elements, we have to look at the equation. Here it is minus 30x1 x2. So this should be split into two terms, which is minus 15x1 x2 and minus 15x1 x2. So this will form our A12 and A21, and then we have A22, which is 17. So as you can see, this is a symmetric matrix. Now we have to transform this into principal axis form, which is q is equal to y transpose dy. This is equal to lambda 1 y1 square plus lambda 2 y2 square. Here D is the diagonal matrix of A, and lambda 1 and lambda 2 are the eigenvalues of A. So the first step is to find the eigenvalues of A. So write down the characteristic determinant and find the characteristic polynomial. So that is A minus lambda I is equal to 17 minus lambda minus 15 minus 15 and 17 minus lambda, which is equal to, we have to find out the determinant, that is 17 minus lambda the whole square minus 15 square. So this should be equal to 0. So let's expand 17 minus lambda square using a minus b the whole square formula. So this will give us 17 square, that is 289, plus lambda square minus 2ab, that is 34 lambda. And then 15 square will give us minus 225. So this should be equal to 0. And after simplification, we will get lambda square minus 34 lambda plus 64 is equal to 0. Now we have to find out the roots of this quadratic equation using this formula, minus b plus or minus square root of b square minus 4ac by 2a, where a is equal to 1, b is equal to minus 34 and c is equal to 64. So the roots will be lambda 1 is equal to 2 and lambda 2 is equal to 32. Now we know the eigenvalues. So the principal axis form, that is q is equal to lambda 1 y1 square plus lambda 2 y2 square, can be written as 2 y1 square plus 32 y2 square, which is equal to 128. So now let's divide 128 on both sides. So this will give us 2 y1 square by 128 plus 32 y2 square by 128. This is equal to y1 square by 64, that is 2 by 128 will give us 1 by 64, and then plus y2 square by 4, which is 32 by 128, that will give us 1 by 4, which is equal to 128 by 128, that is 1. So as this 64 can be written as 8 square and this 4 can be written as 2 square, that is y1 square by 8 square plus y2 square by 2 square is equal to 1. And as you can see, this is an equation of ellipse, that is the conic section represents an ellipse. And to find the direction of principal axis, we need to determine the normalized eigenvectors. That is, the magnitude of eigenvector should be equal to 1. So let's find the eigenvector corresponding to the eigenvalue 2. So substitute lambda 1 is equal to 2 in the original equation. This is the characteristic determinant equation. That will give us 17 minus 2 minus 15 and 17 minus 2 multiplied by the column vector x1 and x2. So again this should be equal to 0. and we will get this equation, that is after doing the matrix multiplication we will get this equation 15x1 minus 15x2 is equal to 0 and minus 15x1 plus 15x2 is equal to 0. And after doing the simplification, that is 15x1 is equal to 15x2 and then x1 is equal to x2. So this will give us x1 is equal to x2. And now we have to choose value for x1 and x2. So in this problem, let's assume our x1 and x2 are equal to 1 by root 2. So the eigenvector will be 1 by root 2 and 1 by root 2. So if you find out the magnitude of this eigenvector, that is square root of 1 by root 2 the whole square plus 1 by root 2 the whole square. So this will give you square root of 1 by 2 plus 1 by 2, which is square root of 2 by 2, that will give you 1. So the magnitude of the eigenvector is 1. So this is a normalized eigenvector. Now similarly, let's find the eigenvector corresponding to the eigenvalue 32. So instead of 2, now we have to substitute 32. So 17 minus 32 will give you minus 15. So minus 15 minus 15 and 17 minus 32, which is minus 15, multiplied by the column vector x, that is x1 and x2. This should be equal to 0. So after writing the equation, you will get this mark. So that is minus 15x1 minus 15x2 is equal to 0. So x1 is equal to minus of x2. So let's substitute x2 is equal to 1 by root 2. So if I substitute x2 is equal to 1 by root 2, we will get x1 is equal to minus 1 by root 2. So if you find out the magnitude, here also you will get 1. Let's form a matrix whose column consists of the determined eigenvectors. And then let's do this transformation. Small x is equal to capital X into small y, which is equal to the matrix 1 by root 2 minus 1 by root 2, 1 by root 2 and 1 by root 2 multiplied by y1, y2. So if you do the matrix multiplication, you will get x1 is equal to 1 by root 2 y1 minus 1 by root 2 y2 and x2 is equal to 1 by root 2 y1 plus 1 by root 2 y2. So this gives us the direction of our principal axis. Now we have to find out the rotation. So this is a 45 degrees rotation. So you compare this result, that is x1, x2 and this degree with the example 1 in section 8.2. So compare the results. So let's see how we got 45 degree. The matrix X, the matrix that is formed by the eigenvectors, is an orthogonal matrix according to the theorem. That is, the theorem states that the eigenvectors of a symmetric matrix forms an orthonormal eigenbasis. So this is an orthogonal matrix. And then this transformation, x is equal to capital XY. This is an orthogonal transformation, that is x is equal to capital A, y. We know that orthogonal transformation is a rotation. So let's compare this with the rotation matrix cos theta minus sin theta cos theta. And from this it is clear that cos theta is equal to 1 by root 2, which means theta is equal to 45 degrees.